Welcome to our second Routing Switching Essentials class. Glad to have you. You see, I've got some things I need to grade, so I do apologize for not having everything up to date and grading. It's always an interesting time at the beginning of courses, so I appreciate some of you getting work done too, because I haven't really even put any due dates on, but I did mention some things, so it's good to have you going. Today we're going to look at Chapter 1 of our Routing Switching Essentials class. Now, I did send out to you the map plan for the way that our classes or labs are now mapped versus what they're named in NetLabs. The good news is I'm hoping that in about 14 days we won't need that. It will actually be already set up to where we can have the exact same names and numbers as what's on in the introduction or the. See, was this it? No, this is the one. That was actually the introduction class. Nope, that's this class. All right, sorry, an aside there. Any questions about the lab so far about getting into the lab? I got this page actually marked wrong. So this is it. So when you were doing lab, when it calls for lab here 1146, that is actually NetLab's lab 4146 for you. So I got to rename this. I got a folder in. But I apologize again. I know that's confusing, but it was either that or teach the old version of the class, and I didn't want to do that. So you have to bear with me as we kind of get through some slight growing pains. Some slight growing pains as we get this going. All right, so I've got that fixed enough in this time frame. So let's talk Chapter 1. Talk routing concepts. Routing is a layer 3 function, so it's a function that we associate with our routers and any device that functions at layer 1 or layer 3. It deals with logical addresses. Okay, so we're going to be looking at, and I usually for these classes don't do this activity. It's something you may want to do in your classroom, because here it is. You know, do we really need a map? And you actually have them go out to Google Maps and find a route between the capital city of your country and some other distant town, so you can actually see a route, and then see if there are multiple routes that could be used. And it gives you a chance to kind of let them see that we already have networks. We have networks that consist of highways. We have networks consisting of phone lines, cable, power, water. Water is a big thing. So that's a good thing to kind of look at, and especially with students who are new and have no experience at all with networking. For our chapter for us, we're going to look at some of the characteristics of a network. So topology, we do know there's two different types of topology from our Introduction to Networks course. In fact, I just went over that in Chapter 1 with that particular class. But there are physical topology, or there's physical topology, and there's logical topology. The physical topology is the way that the devices are physically connected together, whereas the logical topology is the way that information flows on a network. We talk about speed, so bits per second, megabits per second. Cost, how much a network would cost. I'm going to turn off my picture so save some bandwidth and some size on the recording. Security, how secure are our networks. Availability, scalability, and reliability, all things that are greatly affected depending upon how you build your network and what type of network you have in place. So why do we need routing? Well, one of the reasons we need it is because typically between any 2 points on a network, there's more than one path. And there may be a best path now that is not the best path later. We had an instance here on campus last Thursday, I believe it was, where the Metro Ethernet provider for our entire county had a major outage across a huge portion of the county. Well, we had a backup link going to another part of our campus, another campus we had. Well, guess what it used? It used the Metro Ethernet from the provider in our county. So our primary and our secondary even though we have two different internet connections, both got to the same place via that Metro Ethernet. Now, the problem is we don't have a lot of choice. We don't really have the ability to have two different Metro Ethernet connections. So even though we did have two paths, our network went down for a couple hours. And sometimes, honestly, that's what it comes down to. When you look at this cost item on a network, sometimes it's just not cost efficient to be completely and totally available or reliable. You've got to make some trade-offs. So here we see our intermediary devices, the routers and the switches, and they are used to move information between our end devices. And we have an example here of 3 LANs being connected by a WAN. Now, a router is just a computer. That's all it is. It's a specialized computer. It has a central processing unit. It has memory. It has an operating system, and it has storage. Well, storage, memory, same thing. Memory and storage. It's a little different in that it's purpose-built to do one thing. So, in other words, I can take a PC, I can put 2 NICs in it, load Linux on it, put IP tables, put routing, put all the things I want to do, and I can route. I can make a router. I can do the same with a Windows box. I can put 2 NICs in and turn it into a router. But the difference between that and a purpose-built router is a purpose-built router has ASICs, or application-specific integrated circuits designed to do one thing and one thing only. Take packets apart, put packets back together. So they're designed to be specific. That makes them faster, all right? The other thing is all of the systems inside the router are built to support that one purpose. And you even get some special devices, like some firewalls and devices, that have built-in encryption and decryption chips to help with the process of creating VPN tunnels or tunnels to support the movement of information across the internet or across the network. The other item on this is when you look at the different parts of a router, obviously the CPU is very similar to what we'd have in a PC. Memory, there are different types. There's RAM, so random access memory, where the routing tables are stored. It's where your buffers are stored. It's where you have a copy of the running config stored. You have read-only memory, which is where on some routers you have a minimal iOS version, and it's where the bootstrap's contained. NVRAM, which is where your startup config is held. Flash is where your iOS image is stored. By the way, you can remember by saying flash and iOS, they go together. So flash is where your iOS is stored. And some Cisco devices do even have hard drives in them, depending on the device itself. Most time now it's not a hard drive, it's an SSD or something similar to an SSD. So here, random access memory has the running iOS. This is something you need to commit to memory because this is something that could show up somewhere that you might want to know for those purposes. I won't say anything else. So random access memory has the running iOS. In fact, when a router boots, I can kind of show you that with, even though it's simulated, I can take a router and if I pull a 2911 out here and I go to the CLI, this is simulating the iOS being decompressed from flash and loaded into memory. So when you see this on a Cisco router, that means it's taking the image out of flash and loading it into memory so that it can run in RAM. So that's the running iOS. Our running config is there. So if I go into the router and I do if I go into privilege exec mode and do a show run, this is the running config. So this is what's in the configuration at this moment. If I make a change right now, if I make a big T host name example, okay, notice how that changes immediately. I do a show running config, you'll see up at the top that obviously my host name has changed. What would happen though if I rebooted this machine right now? Anybody know? If I rebooted it right now, what would happen? Would I keep the name example?
It's going to go. It'll go back to whatever was loaded in memory. Yeah.
Right. So, and that is the startup config. You'll notice The startup config, there's not one present. So if I make all these changes to the running config and forget to do the following, all those changes are lost. Now if I do a show start, you'll see that we got a host name of example. By the way, let me show you a little trick. I'm going to do config. I'm going to make a change again. Config T line con 0, login synchronous, and then password Cisco. Again, never use this. Login. All right, so I made some changes here, and I want to write this. You know, the command taught in the curriculum is copy, run, start. In the real world, just use WR for write. That's short for write memory, and it will write it. And I could have done it from the. How many of you know about the do command? Nobody? Okay, so watch this. I can actually do this. So interface GI00. Let's say I'm going to put an IP address on it. IP add 192.168.12.10 or .1 255. Sorry, I'm not as fast typing as I used to be. All right, no shut. Now I want to save this config, right? A lot of people would hit Control Z, go all the way out to a copy run start. You can type do WR, and anything that anytime you're inside of configuration mode, if you want to do a command that's typically not a configuration command like do show IP int brief, the do command will let you run that command inside of the configuration mode. So in this case, interface configuration mode. So the do command is a nice little thing to keep you from having to pop out of configuration and pop back in and those types of things. So just kind of throw that out there for you while we're sitting here showing some examples. But all of this, now that I've done it, if I do a show run, you'll see that I've got my passwords in here. And if I do a show start, oops, I type it right. Show, good gracious. It's hard to type with hands that don't work. All right, or don't work as well as they used to. Now you'll see that I've got all this, plus I've got the interface configured because I saved it to my startup config. And if I reload this router now, it will come back up with the information that I put into it. So what I did was I created a running config inside of the iOS. Okay, so in random access memory. Then when I did a copy run start, it saved it to NVRAM. All right. And now when I press return, I got to put in a password because I put a password on the interface, on the console. So read-only memory again has your basic bootstrap program and sometimes a limited iOS depending on the version of the function or the version of the router. Non-volatile RAM holds your startup config, and Flash holds your iOS. Again, Flash, iOS. And it does have some other files in it. Sometimes if you're running things like Voice over IP, Call Manager Express, or other items that can be inside of that Flash. Like if you're running a router as a firewall using IPS intrusion prevention, the IPS signatures will be in Flash. Okay. So here's the back panel of a router. We've got our WIC slots. Okay, this is I think it's a 1941. Yep. We've got this console. Now notice this is a mini USB console, so it's also got RJ45. This doesn't mean they're both able to be used at the same time. One or the other is active. So when you plug into one of these, only one will work. The aux port traditionally was used to connect to a modem to allow for remote reverse telnet. If you can't get in a console on a router because someone put a password on it, many times I will connect to the aux port and see if I can get in, because many times they forget to put anything on the aux port and you can go straight in. Here are LAN interfaces, so these are Ethernet interfaces, and then USB ports, which can be used now to actually load and transfer iOS images to a Cisco router, which is very nice compared to having to do TFTP. So routers interconnect networks. So they do packet lookup. They're going to look in their route tables, figure out where it's supposed to go, and then if they have an available route, forward it and send it on its way. So the thing about a router is it's going to have to look at each packet at least to layer 3, which makes it traditionally slower than a switch, because a switch only looks to layer 2. So at each single router, it will be brought in, taken apart to layer 3, route table lookup, and then repackaged and sent back out. So routers choose best paths. How do they do that? Well, it all depends upon the way they've been set up to route. In the case of a static route, see in this case there's a static route going to 3.0 that says send it to 192.168 or 192.168.22, which is across this link. And then this router does a lookup and finds that 192.168.30 is connected directly and then forwards it. Now, each router, there's some rules about routing. Each router is going to make a decision about the correct route based upon its route table alone. So it doesn't care if where it sends it in the next hop knows how to get there. It's just going to look in its route table. All right? That's a very important thing, because many times you can have packets going somewhere and not getting back. The other thing is, it depends on what routing protocol you use as to how the routes are going to be placed into the route table. We know that this router is going to make its decisions based upon its information in its table. Okay. Just because this router knows how to get to a network doesn't mean all the routers in this internetwork know how to get there. And just because you have a path to the destination doesn't mean there's a path back. So in other words, this PC right here on the left could ping 3.10, and that ping could go all the way here. R1 looks up and had a route. Obviously it had a route. Okay, so it comes here, and it comes over to R2. R2's obviously got a route, okay, to the 3.0 network. So that ping goes out to the PC over here. But when that ping comes back, if you look at the route table of this router, if it didn't have this 1.0 static return route to go back over here, that packet would never come back. So just because R1 knew how to get the packet over to 3.0 doesn't mean R2 knows how to get it back to 1.0. Okay? So those are basically the 3 routing principles. All routers make their decisions based upon their route table alone. The fact that one router has information doesn't mean all routers have that information. And last, just because you have a route to a destination network doesn't mean you have a route back from that destination network. So how does the Cisco router actually make the forwarding process, or how does it use the forwarding process? Now, this is where people get a little bit confused, because routers actually do switching. And in this switching, what they're doing, it's how they move the information from an ingress interface to an egress interface. So that's a switching process. Now, there's a route table lookup here that goes on, and there's a couple ways it can be done. One of them is what's called process switching. Process switching is a very, very old mechanism. And with process switching, every packet that comes in, it has to go to the CPU, there has to be a lookup in the route table, and then a decision is made and it forwards it. All right. Even if all of these packets were going to the exact same network, it would not matter. They're going to do a lookup with process switching. Okay. So it is basically every single packet there's a lookup. With fast switching, which is a common method, the very first packet going to a network, okay, that packet goes in and the lookup takes place, and then that information about the lookup is stored in a fast forward cache. And any other packet going to that same destination would not have to go through the entire lookup process. It would use the fast forward cache. The last and probably the best method is called CEF, or Cisco Express Forwarding. With this method, what happens is the router takes all of the information it learns about in the route table and builds a FIB, or forwarding information base, and an adjacency table. and that table has all the routes already pre-looked up before the packet ever comes in. Then when that packet comes in, it can just pull that information out of the table. Now, they give you a couple analogies on how to kind of think about this. Process switching is solving a problem by doing math longhand, even if it's the same problem. So no matter what, if all these packets are going to the same place, we do the same math problem every single time. Fast switching does the following. It solves the math longhand once and then stores that information in a cache and then uses that for every additional packet going to that network. The last one is Ceph, and Ceph says, look, we're going to solve all these problems ahead of time, and then when the lookup comes in, we don't have to do a lookup. We've already got the answer of where these packets need to go. Does that make sense? Do these three methods make sense?
Yeah, absolutely.
Okay. Most Cisco devices today use Ceph, Cisco Express Porting. Almost all of them do. So, where do I find my iOS and system files? Out of these four, NVRAM, Flash, ROM, or RAM? Remember, I'm pointing at your hint. It's in Flash. Hey.
It's in the, I was saying Flash.
Yeah, it's Flash. Okay. And then the running config. It's in RAM.
NVRAM.
Now, running config is in RAM.
Oh, yeah. Right.
Okay. And again, you can remember that with the running in RAM. Startup's in NVRAM, correct. And then diagnostics and boot instructions are in ROM. Okay.
Yeah.
You need to, these you need to commit to memory, and your students will need to commit them to memory because they're very important. And then it shows the different ports. LAN interfaces are D, aux port is C. You've got console is F and G actually. I don't know why. I just can't. So
F is your mini.
Yeah, mini.
F is your mini port.
Yep. 4 gig flash card slots. By the way, you can't see the flash card, but if you pop this little dust cover off, you can stick them right in there. There's your double EWIC slots, and then here is your HWIC slot where you can put in Ethernet. I will tell you, give you a warning. If you've got some old HWICs, some old 2ASs, be aware that some of the newer WICs, the ones with the double rows of pins, won't work on older 2800 series devices. They will work. It's vice versa. The older ones typically work in the new 29s, but if you got some in the new ones and you try to put them in 28s, they won't work. So, but that's the WICs, the WIC 2Ts, or WIC 2ASs. Okay, I'm not going to go over this packet tracer, but I think a lot of you are turning your packet tracers already. I do want to take a second just to stop. I've done all of the assignments for chapters 1 and chapters 2. Again, don't freak out when you're seeing all these. I'm putting in everything that's available because I'm going to make a shell out of this course that I will then give to you so you can create this course and not have to go through all the pain I'm going through of creating all these assignments. So I will make that available to all of you once the class is over and we get it kind of settled down and have the full version up and going. That would be, I put it on Google Drive, and then you can import that into your courses inside of Netacad, which will save you some time in the future. So, connecting to a network. Well, we're going to look at some of these, some of our different types of connections. Obviously, one of the things, you would be amazed the number of people at the National Skills USA contest who cannot get the default gateway right and therefore lose enormous amounts of points when we try to grade from their PC. A default gateway is the following. It is the closest router port to your PC or your device that's on the same network as you. So in other words, it's how you get out of your network. So this router, R1, this interface is the default gateway for these PCs and this server down here. All of these use that to get out. Okay? So, hey, Will. So you have an IP address on your host. You have a subnet mask, which we all know the subnet mask is used to determine what part of an IP address is the host, what portion is the network. And then a default gateway is how you get out of the network. Now, do you always have to have a default gateway? 99.9% of the time, yes. Okay. The only time you really wouldn't, let's imagine.
Yeah, if it's just a couple computers, you know.
Right. I mean, if you had just a couple computers and they were out here, you know, you had just 3 or 4 computers, and for whatever reason, they were not connected to anything. They were just connected to a switch. You know, it's possible, but it's highly, highly unlikely. Okay. Because one of these is going to go to the internet somewhere. So be aware that it is possible, but highly unlikely. Now, a router typically is its own default gateway. That's something they talk about here, gateway of last resort, simply because the router is going to have, when I really think about a router's default gateway, that's its static default route going out. Here we have our topology with our addressing. All right, showing the different IP addresses and how to do it. Notice that R1 and R2 have no default gateway because they're routers, but the PCs do have their default gateways defined. Now, there's 2 ways we can assign an IP address. One is static, one is dynamic. Statically assigned IP addresses are on devices such as servers, printers, help me out here, y'all. What else could it be? Switches, obviously routers. But they're pretty easy to do. You just go in, put your IP address in, subnet mask and gateway, and then DNS if you need your DNS information in there, which 99% of the time you're going to need DNS. Dynamic IP addresses are set to obtain IP address automatically, and that uses good old Aunt Dora. How many of you heard of Aunt Dora? Anybody know Aunt Dora? DHCP Discover, DHCP Offer, DHCP Request, DHCP Acknowledgement. Okay, this is the 4 steps of the DHCP process. I call it good old Aunt Dora. If you want a way to teach your students, you can say Aunt Dora. Discover, offer, request, acknowledge. PC boots up, it sends out a DHCP Discover. The DHCP server sends out an offer. Hey, here's an IP address you can use. So this is the client. This is a server request or server answer. And then the client says, well, that's a mighty fine looking IP address you got there. Do you mind if I use it? And then finally, the server has to say, yep, you can use it. And that is your IP address for a set amount of time, depending on how long the scope has been set up to allow for the IP address to be used. Typically, I think it's 8 days now on Windows Server, DHCP servers. So it's 8 days. And so, so what? Am I wrong on that, Kurt? But I think it's 8 days.
Sorry,
I think that's what
missed.
That's right.
Oh, yeah, it's about 8 days, yeah.
I think it's 8 days by default for a Windows DHCP scope. By the way, you're going to learn how to do DHCP on a Cisco device, and then I'm going to tell you that 99% of the people in the world use their Windows boxes to do their DHCP scopes. Unless it's at a small office, home office. All right. So here's our LEDs, so device LEDs. Honestly, this is kind of what I teach my students. Green is good. Anything else is not good. You know, and that's a very important thing to kind of look at. But it is one of the things I get so tickled. I saw so many problems in my lab by simply walking up and going, do you have a link light? And they go, no. I said, is the interface up? And they go, I'm like, do a show IP and brief, administratively down, okay? Or the other day I had a very interesting problem, and this happens a lot too. Interfaces were up, but they couldn't ping each other. Well, what it was, they had connected the physical cables wrong. And so it was up, but it wasn't connected to the right interface on the other side. That's where the LEDs don't help you. But you do check it layer 1 and say, hey, do I have green blinky lights? If I got green blinky lights, we can move from there to see what's going on. It's so funny too. Sometimes, you know, I turn the power off on the devices over the weekend to save power. You'll come in on Monday and you'll start doing labs, and people are like, "Well, my stuff's not working." And I look at them and say, "Has it got power?" And then they go and go, "Oh, no." And so it teaches them kind of the, hey, check the simple stuff. So console access. We're going to go and connect from a console to a Cisco device. Console connection is out-of-band management. Okay. You have a serial port or a USB to serial connector. Almost everybody now uses USB to serial connector because we don't have serial ports on our PCs anymore. And we have or we use USB Type B for the mini B USB. And then we connect from that port to the console. And we use terminal emulation software and use 9600 8N1. 9600 baud, 8 data bits, no parity, and 1 stop bit with flow control off. So we need to be able to connect to a switch, and we want to be able to do it remotely as well as locally. What we've got to do is we've got to put an IP address on the switch. The switch is still a device that needs an IP address. It's a little different on a switch versus a router, because on a router we put that IP address directly on an interface. The switch's interfaces are designed to be used by PCs. Now, don't let anybody fool you. There is a way, and you know, I mean, yeah, that's not the way to do it. Let me see if this supports it. And there's probably 3560 on here. Yeah, 3560. I may have to let this thing boot first. But 99.9% of the switch ports in the world, they're not designed to be routable. However, most of them can be turned routable. So if I do a show IP brief, you'll see here you've got all these fast Ethernet. So these interfaces are designed to be connected to PCs. Let me bring them up real quick so we've actually got connectivity. And let's just do fast Ethernet there. And you'll see it going through spanning tree, which we'll talk more about as we go through this class. But you see the ports coming up. All right. And then we'll throw a router out here just so now we've got a router we want to go to out here. And I'm just going to real quickly bring that interface up. But what I want to show you is those interfaces are now up. So if I do a show IP brief, you see that these interfaces are up. So the switch ports are designed to be connected to clients. However, let's say that I wanted to connect and make a port a routable port. Some switches support the following command. Well, not that one. I did tell y'all about my bike accident, right? So please give me a little slack on my typing. My hands are still trying to learn to come back. But there is a command called no switch port. Now, I'm going to turn this back to a switch port to begin with. I'm on this gig interface. If I try to put an IP address on it, it's going to say invalid input. It's going to say, I don't know, there's no command, you know, that you can put an address on this because it doesn't work. I'm a switch port. But if I do no switch port, now I should be able to put an IP address on it. And then now this would actually become a port that could be routable. Typically, however, we don't have this. So on our switches, when we need to put an IP address on the switch, we can't put it on a physical interface. We have to go, I'm going to turn this back into a switch port. We have to go into the VLANs. Now, they're showing you VLAN 1, okay? I'm going to go ahead and do it. How many of you know about the do command? Kind of raise your hand if you know the do command. Anybody know the do command? If not, I'm fixing to make your life much better. All right, so you're inside of config mode and you need to run a show command. So I want to look at the VLANs right now. Typically, you would have to drop all the way out and do the show VLAN. Well, I can actually say do show VLANs, or VLAN, and it will show my VLAN. In other words, you'll notice too, when I get done, I'm still sitting in config mode. So I didn't have to drop all the way back out and back into configuration mode. So the do command, do show IP brief, will allow me to run any command while I'm still inside of configuration mode that typically can only be run at user exec mode. So that do command is a lifesaver. All right. Now I'm going to show you something. By default, all ports are in VLAN 1. Now, they're going to show you to put an IP address on VLAN 1 for management. And then very shortly, we're going to start putting it on a different VLAN IP address, or a different VLAN interface. In the real world, we would never put an IP address on VLAN 1. But for this purpose, we're just showing it to you so that you get a little bit of a inkling of what's going on. So I'm going to put an IP address of 192.168.12.3, 255.255.255.0. Okay. Make sure no shut command, even though I really shouldn't have to do that, but I'm going to. And then I'm going to then do an IP. I'm going to back up one level. IP default gateway. Default task gateway. I'm going to do 192, and I'm just picking the number I'm going to eventually assign to my router, 12.1. Okay, so I got that. But the cool thing about this is now this switch has an IP address on it. If I do a do show IP int brief, you'll see this switch has an IP address of 12.3 with VLAN 1 is up. Now, if I shut down, let me show you something that's a little weird here. If I go interface range, by the way, that's also a command you, if you don't know, you need to learn. And I can do FA 0, 1, 2, 3. Okay. Now I can put in configuration commands for interface for the gigabit or fast Ethernet 0, 1, 0, 2, and 0, 3 all at the same time. So I'm going to issue the shutdown command. Now notice something. Notice that fast Ethernet 0, 1, 0, 2, and 0, 3 went down. But also immediately VLAN 1 went down. So if I hit the up arrow and do a show IP int brief, all of these are administratively down, and this is up but down. And the reason it's down is VLAN 1 can only be up, and in fact, any VLAN interface can only be up if there's a physical interface in that VLAN active. So if I do a no shut, you will see that, guess what? Now VLAN 1 is up. So be aware of that. If I use VLAN 99, one of these interfaces would have to be in VLAN 99 and up. And we'll get to that more as we go along, okay? But this puts an IP address on the switch that allows you to ping it or access it from a PC. Cool, eh? All right, so I think it is. I think it's pretty cool. So let's configure a router. Let's do basic router config, which you did some of in Introduction to Networks. But one of the things we've got to do basic router config is give it a name. So a host name. We're going to secure management access. So we're going to secure access to the console port. We're going to secure access to the privileged exec mode. So enable secret class. What does that secure access to? Anybody remember from intro? That will.
It should be for the. Yeah, go ahead.
For the. Say that again. Sorry.
Should be for the enable for you to get in and manage the switch.
Okay, so the enable mode, or what we call the privileged exec mode. So the mode where you can actually make changes and see more of the commands on a router. So enable secret class would set the privileged exec mode password to class. LineCon 0 would set this would set the password to Cisco and require you to log in. V2I04 with the password to Cisco and log in. That would set the passwords for your telnet session to go to the router, or SSH down the road if you set up SSH. And then this command ensures the passwords are not in clear text in the configuration file. Now this only does a level of encryption that allows you to very easily break it, so be careful thinking this is really a big item of security, but it's good to prevent shoulder surfing and see these passwords. A banner message of the day should be written by your lawyer and your legal representation for your company, and have a very clear statement in it. Never ever have the banner message of the day say welcome, because that has been used to actually get people out of breaking into networks. And then you got to save the config. So do a copy run start or do a write WR, which I use a lot. Okay. Again, a lot of people have never seen, but if you're in a router and you need to write the configuration, we can go enable config T host R1, enable secret class line con 0. By the way, I always put logging synchronous on mine. That helps with when returns happen and things come up, it doesn't mess up your typing. Password Cisco login line. Notice I'm not dropping back and forth between modes. I can just jump straight to it. You can also use the up arrow when things are the same to save time. And now I want to save this config. I can do a do copy run start, or I can do a do WR. WR is the old command, which is short for write mem, which lets you go in and very quickly save the configuration instead of having to do a copy run start. Sorry, my phone's beeping. Putting IP addresses on a router interface. You go into the interface itself. If you want to, put a description on it. Put an IP address on it. Do no shut. By default, all interfaces on a router are in the shutdown state, the administratively down state. On a switch, it's different. On a switch, the interfaces are up. Okay. So that would bring that up. Serial interfaces are a little different because we do have to put a clock rate on them to simulate connection to a DCE. So one side will have to be a DCE link. In the real world, we will not do this. Our clocking will be handled by our ISP's device, whatever we're connecting to. And this day and age, most of it's Metro Ethernet we're connecting into. So some frame relay, in which case the clocking is still provided by the ISP's connection. In our lab, however, we have to simulate that by putting a clock rate on one end and connecting the DCE cable to that side. So when you get your serial cables, you'll actually see one side's DCE, one side is DTE. And so we'll put that cable on there. And I'll bring some of those and actually put them on camera so you can see that. But remember, you still have to do the no shut. So put the IP address in, no shut. Now here's the thing. If this other side is not up, okay, so you've configured R1 and brought this up, and you go to look and say, well, hey, I did a no shut, but my S000 is still down. That is because R2 has not come up yet. And you got to bring this side up before the link will actually come up. IPv6, exact same thing, except we're going to put an IPv6 address in. So when you go in here and look at it, you go to gigabit 00, and you do IPv6 address, IP address that's putting in, and a no shutdown. You may also put a link local address on, like we've done in the past. Here we are on gigabit 01, and here we are on S001. So same thing. You'd still put a clock rate in. You'd still put in the IPv6 address. Now, there are some protocols out there, routing protocols in particular, and there are sometimes that you need an interface or an IP address to be on a router that will not go down regardless of whether or not the interfaces, the physical interfaces actually go down. We can use what's called a loopback. Now, loopback is like a virtualized interface or a logical interface. You can put an IP address on it. You can use it to advertise networks, to test advertising of networks. We use it for all kinds of things in a Cisco environment. So just be aware that you will see it being used for many different things, everything from a router ID for OSPF and EIGRP, and to, again, just testing out routing protocols to see if they're advertising certain networks. But just do interface loopback 0, IP address 10.0.0.1, whatever address you want on it. I always get the question, how many loopbacks can you have? The current state is about 4 million is what's allowed per router. So I don't think you really need that many. So we want to look at our interface settings. How do we do that? This is one of my favorite commands and solves a lot of problems. Show IP interface brief. The only thing I wish they would do, and I don't know why Cisco has not done this, is I wish they would give me the subnet mask right here. Just do a slash whatever and give me what the mask is. You give me the IP address, so just please tell me what the mask is. So be aware it can verify there's an IP address, but it can't verify someone's put the correct subnet mask on it. For that, you have to do a show interface gig 00 and drill down and see the actual mask. It will tell you though if it's up, okay? So is the layer 1 up and is layer 2 up? So you can get a lot of information about your status here using that command. Show IP route will show you the connected routes or the routes in the route table. Notice that for iOS version 15, you do have both a connected route and a local route. And that local is used to give you the IP address that's on the actual interface. You can do a show running config, interface gig 00, which would drill down and show just the information for gig 00. I do teach my students that show running config is not a troubleshooting command most of the time, but sometimes you do need to drill down and find some things in the running config. And so that's our commands there. And IPv6 is put IPv6 in front of all those commands. So IPv6 interface brief will give you information about all your interfaces. Show IPv6 interface gig 00, which should drill down on information, IPv6 info on that interface. You'll notice too there's multiple addresses typically on an IPv6 interface. There's not just one IP address, there's multiples. Show IPv6 route shows you're connecting local, same way. And you can just ping. You can use ping to ping, and it's actually typically I do ping IPv6 or ping v6. So here's where you can filter the show command, which is kind of neat. If you only wanted to see what was in the line VTY section of the running config, you can do show running config pipe section line VTY. You can do begin and then put in the words that you want, and it'll start at that part of the running config. So a lot of the same commands you'd use in Linux, you can do that. So show IP interface brief pipe include up would only show you the interfaces that were up. Okay. Show IP interface brief pipe exclude unassigned would take out any unassigned interfaces, so anything that has no IP address on it. Show IP route pipe begin gateway would start with the gateway part of the routing table, which is actually up at the top. And so you can actually do the line con section. So you could do the show me here. It's going to do show running config pipe section line con, and then it would start there and only show you that. It's kind of nice because it speeds things up. It makes it where you don't have to look tab down or space down through the entire config to see what you're looking for. Command history, you should have noticed when I was doing some of these things that as I was doing commands, I would use the up arrow. Show IP brief, show VLAN, and then you can see I can actually go up, hit the up arrow, and it has the history of the commands. Okay, here it says terminal history size 200 would keep up to 200 of my last commands. That's a way to speed up things using the up or down arrow, or you can do Control P, Control N. Typically, we just do the up and down arrow. You can also do a show history to show what's in the history. If you forgot what you typed or you don't know, hey, what command have what have I actually put in here? You can do a show history and get it, see all the commands you've typed. Okay. And then we've got a very basic lab in Chapter 1, just doing basic iOS configuration. This is the lab, by the way, again, that is not 1146 inside of NetLabs. It's 4146 or 4446. I sent that out in an email to you showing how those are going to be mapped for this course. Here, look at this. This is how a router works. A device sends in a packet encapsulated all the way up to layer 7. Goes to the router, it gets de-encapsulated up to layer 3. Route table lookup and decision is made, it then gets forward, and it gets repackaged for whatever media is being used between these two devices. And it gets de-encapsulated, then re-encapsulated and repackaged. So this is Ethernet, this could be HDLC, and then same thing till it gets to the destination where it is repackaged and sent out to the destination. So when it talks about switching, means moving packets from source to destination. So it's literally being switched from an ingress to an egress using one of those methods, fast switching, process switching, or SEF. Excuse me, process, fast, or SEF. And it will be using SEF for our purposes. So, sending a packet. PC wants to send something. It wants to go over to PC2. It would actually compare the destination IP address to its configured subnet mask and determine that PC2 is not on its same network. It would then send it to the default gateway that's been configured. It actually sends out an ARP request, and the ARP request cannot be answered by PC2 because it's a broadcast, but R1 can answer that ARP request. And so R1 acts as a proxy ARP for PC2. And so when you go back here, you'll see, let me pull it back right there. You look in the ARP cache, PC1 says PC2 is on a different network. I'll encapsulate it and send it to my network. Let me find out what the MAC address is. So it sends out an ARP request. Well, the router says, well, that's an ARP request for a non-local IP address. And so it responds with the MAC address of its interface on that network. That allows PC1 to finish writing this packet, to have a destination MAC address for this particular packet. That packet then comes into the router. The router then looks at it and says, hey, let me see where this needs to go. Takes off the data link information, checks all the header information, checks some. Then it looks at the destination IP address and says, what network does that need to go to? It looks in the route table, finds in this case a route, and it says that needs to go out F01 to this next hop IP address. It then rebuilds the frame, okay, so substitute the MAC address for 01, and then the destination MAC address would be 00's MAC address, okay, because it knows the next hop is 22, so that's what it looks for in its ARP table. And now it's going to rebuild the packet, and it's going to forward it out to R2. And at this point, R2 is going to make, see, it's going to send it out. R2 now makes the same process, or does the same process. So I'm not going to sit and go through all of it, but it does the same process. Eventually it reaches the destination, so you can go through this and look at it. But at each individual hop, there's a lookup and a rewrite. So there's a lot going on when you send something across the internet. And this is really the packet forwarding decision. Packet arrives, you look in the route table for a match. Does it match the destination IP address and subnet of a directly connected interface? If so, check the ARP cache for the host it's destined for and send it out. If not, does it look for a remote network? Yes, and there's actually a route, and encapsulate it and forward it. If it doesn't match a directly connected or remote network, is there a gateway of last resort? In other words, is there a default route on the router? If there is, send it out. If not, it goes in the bit bucket. And you get a destination unreachable address or unreachable message, ICMP destination unreachable, back to the sending host. Now, how do we determine our best path? Well, it really comes down to the metric used by the routing protocol that's in use. Now, the best way to think about metric is how do you decide where you go eat lunch? You've got several different things. How much does it cost? What kind of food is it? How's the service? One of the things for me is how far is it from campus? I eat at a little restaurant that's not far from campus at all, and the food's okay. It's pretty good. It's cheap. Service is pretty good, but it's also real close to campus. So those are my metrics that I use when I go to decide where I'm going to eat. Well, routing protocols use different metrics in deciding the best path. Some of them use an item called hop count, which is just however many routers it goes through. Okay, each router is a single hop, and we're going to pick the route with the fewest hops. And if that's what's being used, then the best route would be across this 56K link, which should not be faster than this link across two T1s. So if it's using bandwidth, it'll actually go across the two T1s. So depending upon the routing protocol, we'll decide upon the actual path being used. RIP, a very simple routing protocol, uses hop count. OSPF uses cost. And EIGRP uses, as they say, bandwidth, delay, load, and reliability. It really comes down to bandwidth plus the sum of the delays for EIGRP, and you'll learn more about that as we move forward into other classes. But just be aware that the metric is how a routing protocol determines the best path. Load balancing is the ability to load balance across equal cost or unequal cost paths. In this case, these would all be equal cost paths, so you can load balance across it since they're all the same distance. EIGRP will actually do unequal load balancing. That's down the road. We'll talk more about it. Goodness gracious, it's 6 o'clock. I'm going to go a few more minutes and try to get as close to finishing up as I can. Yeah, we're not going to be able to finish it up, I don't think. Yeah, we're close. No, we're not going to be able to get there. All right. Actually, folks, I'm going to stop right here at administrative distance. Are there any questions? The chapter's a little longer than it used to be in this version. I'm going to stop the recording.